Okay, so I want to make a recording of the rotational kinematics review sheet. And the very first problem says that you have a car on a Ferris wheel with an angular displacement of 0.34 radians. So 0.34 rads is your theta. And then it tells you the car is going to move through an arc length of 12 meters, so S is equal to 12 meters. And they want to know what is R. Well, if theta is equal to S over R, then R is equal to S over theta. S is my 12 meters. My theta is 0.34 rads. So when I divide 12 meters by 0.34 rads, I wind up getting 35.3 meters, if I can read that correctly. Yes, 35.3 meters. So the radius is 35.3 meters. So there's number one. All right, number two says that we have an object that is rotating, and it's actually a phonograph record, and its initial speed is 33 revs per minute, so that's omega I. And then omega F, it builds up the speed, or does it slow down? Let's see. It slows, so that's 11 revs per minute. And in doing that, it takes 2 seconds. So you can already see we have some issues. We have minutes here and we have seconds there. So I'm going to go ahead and change that to 33 revs every 60 seconds. And that's going to give me 11 revs every 60 seconds. So when I divided 33 by 60, I got 3.0, and I went ahead and converted it to rads, but I don't think it tells you. No, it doesn't insist that you change it to rads. So I can leave my 33 revs. Well, let's just be a little more exacting than that. So if I'm looking for alpha, alpha is change in omega over change in time. So that's 33 over 60 is my omega I, but I want to start with my omega F. So that's 11 over 60, and that's revs per second, minus 33 over 60 revs per second. Oh my gosh, got some issues. And it's going to take 2 seconds for that to happen. So when I solved it, I solved for radians per second squared, but we ought to be able to do this. That's going to be a negative 22 over 60 on the top, divided by 2 on the bottom. So that's negative 22 over 60 times 1 over 2. So that's going to be negative 22 over 120. So you can reduce that down, and that would be your revolutions per second squared. However, it's negative because you're decelerating. When I did it in radians per second squared, and I got 1.15 radians per second squared. So let's see if that's reasonable. This is 22 over 120. So that's what, 11 over 60? Yeah, that's going to work. Okay. So you don't need to do it both ways, but you can check my math, make sure I'm good to go. And then they wanted to know what was the angular displacement during that time. So that's part B. So theta is equal to omega F squared minus omega I squared over 2 alpha, or you could say, yeah, that's probably the best way to do it. So omega F was the 11 over 60 revs per second. Don't forget to square it. Minus 33 over 60. Don't forget to square that. And then I'm going to divide that by my 2 times negative 22 over 120 revs per second squared. And again, I didn't do mine that way. I did mine in radians, and so when I got my radians, I got 4.63 rads. But you can easily convert rads to revs and check yourself. All right, number 3. Number 3 says a tire placed on a balancing machine in a service station starts from rest, so omega I is 0. And then I want to take it up to a final angular speed. And I know that theta is 4.7 revs. And I also know that it takes 1.2 seconds for that to happen. And they're looking for alpha. That's kind of sad looking. Let's fix that. So I know that theta equals 1/2 alpha t squared plus omega it. That's 0 because it tells me that it starts from rest. So I'm going to have 4.7 revs is equal to 1/2 alpha times t squared. Don't forget to square your time. That's 1.44. Half of that is 0.72. So what I'm really going to have is 4.7 revs divided by 0.72 seconds squared for my alpha. Now, when I did it, let's see. Oh, of course, I went to radians because that's what I always do. So I got 20.5 radians per second squared. 20.5 radians per second squared is equal to alpha. So you can take your revs per second squared and check up my radians per second squared. Now on the test, if we want to be really picky about that, we will tell you exactly which one to go to. If we don't tell you to give us the acceleration in radians per second squared, then I wouldn't worry about it. I would just work it in whatever units I wanted. Okay? All right, the fourth one, I think I want a new ink color. Let's go with green. So the fourth one says that we have a small pebble that breaks loose from the treads of a tire. The radius of the tire is 32 centimeters, 0.32 meters. And I know that the tangential speed, which is just the linear speed on a tangential line, is 49 meters per second. And they want the angular speed, omega. Now, omega, actually what I typically would use is V equals omega R. So V divided by R would be equal to omega. So V is 49 meters per second. I'm going to divide that by 0.32 meters. Notice that my meters will cancel, and that will give me my radians per second. And when I did that, I got my radians per second to be 153. Okay. Number 5. Number 5 says that we have a building superintendent who twirls a set of keys in a circle at the end of a cord. Keys have a centripetal acceleration of 145 meters per second squared. Cord is 0.34 meters long. We want the tangential speed. So let's write down our given. So our centripetal acceleration was 145, and I believe it was expressed in meters per second squared. And then we know that the length of the cord, or the radius of the circle that he's spinning it in, is 0.34 meters. And we want to know what is the speed, tangential, which is just normal speed for us. It's just on the tangent line. Well, AC is equal to V squared over R. So AC times R, take the square root of that, that'll give you V. So I know that V is equal to the square root of 145 meters per second squared times 0.34 meters. So when I did that calculation, I got a value of 7 meters per second. All right, I'm going to stop there.